Jupiter's moon Europa contains more than twice the volume of all Earth's oceans combined. Despite being smaller than our moon, this hidden ocean has existed beneath miles of ice for potentially 4 billion years, longer than complex life has existed anywhere on Earth. While we've spent decades scanning distant exoplanets and drilling into Mars, we may have overlooked the most promising habitat for life in our own solar system. The question isn't whether Europa has water. The real question is whether we've been searching in entirely the wrong places for the past 50 years. For 5 decades, the search for life has focused on Mars, distant exoplanets, and places that look like Earth. But new evidence suggests Europa's ocean has been stable and potentially habitable longer than complex animals have existed on our planet. NASA's Galileo spacecraft proved this ocean exists through magnetic field measurements taken during 14 years of observations. Europa generates its own magnetic signature as the moon orbits through Jupiter's field, creating a detectable electrical response that indicates a conductive layer beneath the surface, most likely a salty ocean. Recent thermal models show this ocean likely formed within the first few 100 million years after Europa's formation and has persisted for billions of years. We're about to find out if our 50-year search strategy has been fundamentally wrong. Europa orbits Jupiter every 3.55 days in a gravitational dance with Io and Ganymede that continuously flexes the moon by tens of meters. This flexing generates approximately 2 trillion watts of internal heat, enough to power the entire United States for about 6 months, all focused on keeping a global ocean liquid beneath 15 to 25 kilometers of ice. Imagine squeezing a rubber ball in your hand repeatedly. The friction creates heat. Jupiter's gravity performs this same squeezing motion on Europa every orbit, but with forces so immense they flex solid rock like putty. Juno spacecraft data from 2022 provided new measurements of Europa's ice shell thickness, estimated at 15 to 25 miles thick based on microwave observations. The ocean beneath reaches depths of 60 to 150 kilometers, making it deeper than Mount Everest is tall and dwarfing Earth's deepest ocean trenches. Magnetic measurements prove this ocean is salty, with connectivity levels matching Earth's seawater. Unlike Earth's oceans that would freeze solid or boil away without our atmosphere, Europa's ocean remains protected by its ice shell and powered by Jupiter's relentless gravitational pull. Thermal evolution models by Sotin and collaborators in 2023 show this ocean likely formed from water released as Europa's rocky interior slowly dehydrated over hundreds of millions of years. The process began when radiogenic heating from uranium, thorium, and potassium decay warmed the interior enough to drive water from hydrated silicate rocks, creating serpentinite minerals and releasing vast quantities of liquid water that migrated outward to form the current ocean. Picture a wet sponge being slowly heated. The water doesn't disappear. The water moves to where conditions allow it to exist as liquid. Complex animals on Earth first appeared 540 million years ago during the Cambrian explosion, when life suddenly developed eyes, shells, and sophisticated body plans. Even the earliest eukaryotic cells, the building blocks of all complex life, only emerged around 2.3 billion years ago. Europa's ocean has likely existed for 3 to 4 billion years, meaning this alien sea was already ancient when the first complex life appeared on Earth. The implications stagger the imagination. While Earth was still a planet of simple microbes, Europa may have already hosted a mature ocean ecosystem for over 1 billion years. For more than half of Earth's history, life remained strictly microbial and anaerobic, surviving on chemical energy in dark environments where sunlight never penetrated. Europa's ocean provides exactly these conditions with mathematical precision. Perpetual darkness blankets the seafloor. Chemical energy flows from water-rock interactions. Stable temperatures hover just above freezing throughout the ocean's depths. The seafloor pressure of 1,000 bar falls well within the tolerance range of Earth's most extreme deep-sea microbes, organisms that thrive in crushing depths where no surface creature could survive. Recent studies show Europa's rocky mantle remains relatively cool and hydrated, continuously releasing hydrogen and other chemicals that could fuel metabolism for billions of years. While Earth's surface life depends entirely on sunlight captured by photosynthesis, Europa's potential biosphere would mirror Earth's earliest microbial ecosystems. The same serpentinization reactions that may have powered Earth's first life forms, where water reacts with iron-rich rocks to produce hydrogen gas, could be occurring on Europa's seafloor at this very moment. These reactions require no sunlight, no organic compounds delivered from space, and no pre-existing biology to jumpstart the process. Serpentinization represents one of the most fundamental energy sources available to life anywhere in the universe, and Europa's ocean floor provides the perfect chemical laboratory for these reactions to proceed continuously for geological ages. NASA has spent $2.7 billion on Mars rovers searching for ancient water that dried up billions of years ago, leaving behind only mineral traces and empty riverbeds. The James Webb Telescope scans thousands of exoplanets light-years away for atmospheric biosignatures, searching for oxygen or methane in alien skies. But Europa's ocean contains more water than Mars ever possessed during its wettest period, and this water remains liquid today, not frozen in polar ice caps or lost to space. Europa's surface receives radiation doses of 5,400 rads per day, levels that would kill unshielded organisms within hours. But this same radiation produces oxidants that get mixed into the ocean below through complex ice dynamics. Laboratory experiments conducted at the Jet Propulsion Laboratory show amino acids, the building blocks of proteins, can survive Europa's radiation environment when buried just 10 to 20 centimeters deep in ice. The Hubble telescope has detected possible water plumes erupting from Europa's surface, towering 200 kilometers above the Moon's south polar region and offering direct access to ocean material without drilling through miles of ice. These plumes, if confirmed by upcoming missions, could carry biosignatures directly from the subsurface ocean to where spacecraft can sample them with existing technology. Europa Clipper, launching in 2024, will map these plumes and analyze their chemistry during 49 close flybys planned over approximately 4 years of operations in the Jupiter system. The spacecraft carries 9 scientific instruments specifically designed to measure the ocean's depth, salinity, and chemical composition with unprecedented precision. Unlike Mars, where we search for fossils of ancient life, or exoplanets, where we can only analyze light filtered through distant atmospheres, Europa's ocean remains accessible with current technology and may have been continuously habitable longer than life has been complex anywhere in the universe. The radiation environment that makes Europa's surface so hostile also drives a complex chemistry that could benefit life below. High-energy particles split water molecules in the ice, creating hydrogen peroxide and oxygen compounds that eventually work their way down to the ocean through convection and ice turnover. This process has been operating for billions of years, potentially building up large concentrations of oxidants that could support metabolism when mixed with hydrogen from the rocky seafloor. Europa basically operates as a giant chemical reactor powered by Jupiter's radiation and gravity, producing the exact ingredients that life requires. We've been looking for life in places that resemble Earth's surface. But life on Earth began in dark, chemical-rich environments much like Europa's ocean. If Europa's 4-billion-year-old ocean hosts even microbial life, the discovery would represent the oldest continuous biosphere we've ever encountered. The ocean has persisted through impact events that would have sterilized planetary surfaces, through changes in Jupiter's radiation environment, and through the gradual cooling of the solar system itself. Europa's potential for life doesn't depend on a perfect distance from the Sun, a protective magnetic field, or a massive atmosphere like Earth's. The Moon depends only on Jupiter's gravity, rock-water chemistry, and the basic physics of tidal heating. These conditions exist throughout the outer solar system, on moons around Saturn, Uranus, and Neptune. If life exists in Europa's ocean, the discovery would suggest that habitable worlds may be far more common than we've assumed, hidden beneath ice shells around gas giants throughout our galaxy. The search for life may not require traveling to other star systems or terraforming Mars. The search may just require looking beneath the ice of a moon we've known about since Galileo first pointed his telescope at Jupiter 4 centuries ago. Europa Clipper will arrive in 2031, and for the first time in human history we'll have detailed data about Europa's ocean and potential habitability. The next decade will determine whether Earth's oceans are unique or whether life flourishes in alien seas that dwarf our own, seas that have existed since before complex life began anywhere in the universe.